Hey folks, Emily here. Today you are going to learn how to build a retrieval augmented generation system on Amazon SageMaker. So let's get started. All right. So what on earth is retrieval augmented generation? So let's break down these three words. Number one, retrieval. The word retrieval, of course, stands for going and grabbing a document. It's commonly associated with search. So a search system can also be called a retrieval system. The idea is that you have a number of documents stored in something like a database, and then your retrieval process goes and tries to find the right document. Usually you're trying to find the right document based on something your customer is asking. So a customer asks a question, and then the retriever is going to go and find that question. Second word for you, augmented. And so what we're augmenting is we're taking that document. So the customer asks a question, we go and we look up a document from a database, and we're going to use that document to augment the generation from the large language model. And so that's retrieval augmented generation. We're looking up a document based on a question that comes in from our customer. And then we take that document, we're going to send the whole document to the language model, and we're going to ask the customer's question at the bottom. And that's what you see in this visual here. Essentially, we're prompting the language model with our entire document. We're sending in the whole document as large as we can, depending on the context size of the model. We're going to add a couple things. So let's break this down. So first, we're adding in, same as last time, the guidance to the model. This is like the high-level setting with the model that tells it, you are a assistant, gives it high-level information about how you want it to respond. So you provide the guidance. And then the second is the context. So the context is that document, right? We go and we retrieve, or we look up, or we search for a document in the database. Once we have that document, we are going to put that directly into the string. And so here it's just really a regex insertion. We're just inserting that entire document into this gigantic string here. So that's the context. And then the third is the instruction. And that instruction comes directly from the customer, right? So the customer shows up, they ask a question, we go and we look up a document based on that question, and then we take the document, we insert it into the prompt, and then we're also going to insert the customer's question. And so that's this third component that you see here, this question, is we're inserting both of those into the prompt. And so we're sending all of these to the language model and getting a very informed response back. Let's see what this looks like a bit more broadly. So again, your customer is asking a question, and they're going to be asking a question through some sort of web application. This might be a Streamlit app, might be a Gradio app, it can be a Node.js app, it can be a React app. Any type of application you are developing, your customer is going to ask a question. They ask this question, and then you're going to route that question through some type of lookup service. There are many, many different options for looking up questions. In this case, this is a vector database created with Amazon OpenSearch service. And so that's one candidate option for using vector stores. The reason why we care about vectors here is because when you go and ingest documents into this vector store, there's this offline process that you do ahead of time. So you start with your documents, for example, in your S3 bucket. You're going to create embeddings with those documents. And so you need another model to actually generate embeddings for this. So you might use, which is what we're going to do in the demo, you might use a SageMaker endpoint that's hosting a model to generate embeddings. Actually, it's still a large language model, believe it or not. The first 75% of that model is the same as every other LLM, but the difference is that the output, instead of outputting text, it's outputting a vector, actually. So that LLM, the embedding model, is taking a document and it's creating what's called a dense representation of that document. That's also called an embedding. So we create this embedding, which is sort of a dense representation of the syntactical meaning of what's in that document. And we're going to get these embeddings for the entire database. So our whole document store, essentially we're going to convert all of those documents into these lower level representations, which is the embedding. And then the embeddings are what make it into the database. So then the database or the vector store, I mean, it's called a vector store because it's holding vectors, it's holding the embeddings. Remember, vector is just a really long list of numbers. And so this OpenSearch database essentially is holding all of those dense embeddings or representations for you. And then there are lots of different ways to handle this lookup, which is where your customer asks a question, and then you want to go and look up the right document based on the customer's question. Most of the time, what you're going to do is you're going to take the customer's question, and you're going to route that question through an embedding endpoint, for example. So you're going to take that question, convert that into an embedding, and then do like an embedding similarity lookup. Basically, that's going to do like an approximate k nearest neighbors and just extract the, handful of vectors that are most similar to the customer's question. Now, this will vary based on the vector store that you're working with. Some of them let you handle more of this, some let you handle less. So you have a lot of different options for how to dial in that retrieval step, again, where you're just trying to find the right document using embeddings coming out of LLMs to do that. Once you actually have that document, that's the hard part, actually. The hard part is just grabbing the document. Once you have the document, then you're doing the same sort of prompt concatenation and then invoking the endpoint as you've always been doing. So you're going to grab that document, put the document into the prompt along with the customer's question, and then just send it straight to the LLM to have it read the document, ask the question, and then answer the question appropriately. And so this is one way that you can build a retrieval stack using SageMaker. Now in the demo, we're going to one-up this. So in the demo, I'm going to show you a multimodal retrieval augmented generation stack. So multimodal here, of course, refers to multiple modalities, where a modality is like image and text, for example. So two different modalities. And what we're going to do is we're going to build a multimodal retrieval stack just in your SageMaker notebook. So something really small that works with Amazon Science papers. So I downloaded a handful of some of the latest papers on Amazon Science. And then I'm going to use LangChain and SageMaker endpoints to build a local multimodal retrieval component for that. It's going to run ChromaDB on a SageMaker Studio notebook, and then we're going to be able to look up documents for this based on the content of the paper, both in the language and in the summary of the images that was generated by Lava, where Lava is another model that does large language and vision analysis combined. And so that's what we're going to run through right now. So let's check it out. All right, so just as usual, we're going to start in SageMaker Studio. Actually, when I went to do this, I needed to use Studio Classic, as it turned out. So if you didn't know this, in SageMaker Studio, you can run a number of applications, including the new Jupyter Lab and also SageMaker Studio Classic. And so it turned out that I needed to run Studio Classic for this one. So that's what I'll be using. I also created a number of endpoints. So in the deployment section, we can look at these endpoints that I have running. So I have two models that are hosted on SageMaker endpoints. One of them is a Llama 2 70B chat. This is the large model that will be answering the questions of the customers based on that document that comes in through the retrieval stack. And then the second model is the embedding. This is a GPT-J 6 billion parameter model that takes language and then converts that into a dense representation of that, which is the embedding. And then, of course, I use SageMaker Jumpstart to deploy those in clicking. It was very fast. It was delightful, very reliable. Those endpoints were up and running in minutes. So the notebook I'm using, this is heavily reliant on the LangChain cookbook. So the LangChain open source repo has a cookbook with many, many different solutions. I took a look at one of the solutions, which was multimodal retrieval, And then essentially this notebook is a modification of that to work nicely with the SageMaker components. So CJ, thank you for the source code. I hope you enjoyed this SageMaker demo. And so feel free to follow along with me. Again, this is available publicly, so if you'd like to download this notebook and then step along with me, you are welcome to do that. Let's check it out. So again, as promised, here I am in SageMaker Studio. And then there are quite a few instances that you are going to need to run this. Let's see what they are. So in the notebook, I tried to list them up front, so you know. So there are really 3 GPU machines that you're going to use here. The first one is for the notebook. So the model that's going to work with images is called Lava. And this Lava model is actually running on Studio locally, actually. It's parked on a local G5.2 XL machine. So the first thing I did when I opened up SageMaker Studio Classic was go in and make sure that I'm running on the right machine. So I actually turned on this G5.2 XL, and then that's where my notebook is parked. And then just as I mentioned previously, then I turned on 2 extra endpoints. And so one was for the large language model that's going to be chatting with me, and that's the G5 actually was what I used. That was a G5.48 XL. And then the third one was the G5.12 XL that's hosting that embedding model. And then remember, I'm going to use that embedding model to create these dense representations or embeddings of the documents, and then those documents are what go into my ChromaDB vector store. There are a lot of requirements for this notebook, so plan on spending a lot of time installing and upgrading pip, getting all of the requirements downloaded. When I ran into issues with different versions, I tried to just pin it. So for Lava, make sure you're using transformers at least 4.39.1. Bodo 3, you want to hit at least 1.34.23. And then make sure you definitely have this OpenCV Python headless that gives you some of the lower libraries that we're going to use to parse the PDFs. And then lots of others, SQL Alchemy, Flask SQL, so get those installed. Update apt-get, install all of the rest of these apt-get packages. These other packages are what are going to let us parse the PDFs, actually. So this notebook is going to take PDF files as an argument, and then we're going to parse those into text, tables, and images. And so these lower level libraries are what let us do that processing. So once you have those downloaded, go ahead and restart your Jupyter kernel, just so you know that you definitely have the new packages and that they actually did install. And then to check, so your transformers version, you want to make sure you have at least, again, that 4.39.1. And then make sure you can import this function in particular. So the library we're going to use to parse the PDFs is called unstructured. So it's unstructured, this open source Python package. And then we're going to use this partition PDF function. This can be finicky, so really don't go on to step 2 until you've actually gotten successful imports on those parts in step 1. Okay, so once you're done with that, then we're going to download Lava again to this notebook, and we're going to test it locally to make sure it's working. So again, unless you have the recent version of the Transformers SDK, that import will not work. It will fail. So just update it. Make sure you have the right one. Once you do, then this was the Lava version I used. So v1.6. And then, so Lava has both vision and language components, and I've seen different options that switch out the language backend. So this is a Mistral 7B language backend. So that's here. And then just like normal, you need the processor, which is basically the tokenizer, except it's processing bytes and images. And then, great, so we set that. That's gonna load. And then to test Lava, go ahead and download an image. I got an image from the Lava paper, which I thought was fun. So Haoshin Lu, thank you for the JPEG here. I got this directly from your GitHub page. And then this is what we call a radar plot. So we looked at this radar plot in the video in this series on evaluating language models. Honestly, I think radar plots are a really helpful way to visualize many different benchmarks that are all sort of normalized in similar ranges. So if they're all normalized in, say, like 0 to 1 or 1 to 100, and then you want to know basically how different models are performing on all of these dimensions, then the radar plot is a really nice way of just representing that information. And so here's a radar plot for different models that are doing visual question answering. So the lava model is right here, 1.5, and you can see clearly that has the most surface area, so that's hitting the best performance on the benchmarks as compared to these 3 other models. Let me zoom back in so you can see the rest of the code. All right, and so go ahead and get this image, and then once you have it locally, we're gonna read it into this image package, and then, so the prompt that you're gonna send to the model, it is quite opinionated. It needs to see this instruction square bracket, so it needs to know what the instruction is. And then it also, for the prompting to work, you need to have these tags here for image, and then the syntax below is going to insert the image into that line, actually, and then both of those go to the Lava model. When I was testing this, I could see that Lava was good at understanding sort of like really basic questions or really very introductory questions. So something like, what is shown in this image, or what is the meaning of the image? But once I started to ask for specifics about say like which model covers the most surface area in this plot, which models are shown in the legend, which models has the least surface area in the plot, I mean, it was absolutely not accurate. And so I just thought that was an interesting note. So we take the processor and we send the prompt and the image to the processor. We're gonna drop that to CUDA, so that's on the GPU. And then the model actually is already on the GPU because of bits and bytes. And then that's gonna generate a response using the inputs. And then we get this. So here's what Lava thinks is in the image. Image is a radar plot. Multi-dimensional plot displays values for multiple quantitative variables. All right, and then it gets some of the axes, so such as MMM-vet, MMM-bench. Let's just double check that it was triple M. Ah, it was only a double M. so Lava was hallucinating an extra M here. But I mean, it was pretty close. All right, great. So we downloaded Lava to this notebook, and then we tested it to make sure it's mostly working. The next thing we're gonna do in step 3 is we're going to ingest these local PDF files using this unstructured library. So again, that unstructured library is going to use this partition PDF function, and then from LangChain, I'm importing this character text splitter that's going to work nicely with both of these. And so this partition PDF takes the file name, max characters, and a chunking strategy. And then essentially this helps with the process. And so in the file path, point to the papers, and then within the papers, we're gonna add in the PDF. And I think I am doing one PDF, actually, looks like. So let's look at this PDF here. So that's out over here in the papers directory. Yeah, and so here is this meaning PDF that again I got from Amazon Science, where it's looking for the meaning representation from trajectories in autoregressive language models. And so that's a paper from back in November. And then just to give you a sense of what this unstructured library is going to do. So it will grab the text and it will sort of, it's going to take the PDF and it's going to break it into 3 parts. One part is just the raw text. The second part is a table. And then the third part are the images. And so this is an image that this unstructured library will actually write as a figure. It's going to write a new file in my working directory with these images, and I'll show you that in a second. And so we get the body of the text out of the unstructured, and we also get the tables. I don't think unstructured is going to do a good job of like extracting the equations in a meaningful way or extracting the algorithms in a meaningful way. So that's future work for someone to pick up. But nonetheless, yeah, this table, for example, will be well extracted by that unstructured library. So nonetheless, that's what we have. So we get the raw PDFs, we categorize them, run the text splitter, setting the chunk size. So for the chunk size, make sure that is small enough to fit in the context window of your model. So if you're using the Llama 2, then you want the chunk size to be definitely under 4,000. And I just did 2,000 to make the example here easier run. Okay, and so then we'll have the tokens. And so here is just an example of the first text that was split. And so, yeah, as promised, here we go, meaning representations with the authors, and then they discuss it. So definitely we extracted that text logically. Step 4 is we're going to set up LangChain with our SageMaker endpoints, and we're going to generate text summaries. So we're going to go summarize. We're going to use the chat model that we hosted to summarize the text. And so we've got all the imports. So again, from LangChain, we're importing the SageMaker endpoint. Then we have this chat prompt template, and then the content handler. So we looked at this last time. Your content handler, remember, is another class just to lightly modify to point to your SageMaker endpoints from LangChain. And if you're working on a Llama 2 model, then just make sure that your output looks like exactly like this. So first index 0, and then generated text as a key. All right, and then so we'll point to Bodo 3, again using the SageMaker runtime client. We'll start with this template, and then we're going to take that template and then load that into LangChain. So we set that into the chat prompt template. And then we have the content handler from that class we defined above. And then here we're pointing to the SageMaker model. So a couple things to call out here. The endpoint name, this is obvious. That's the name of the endpoint. The inference component name might be a little bit hard for you to find. So let me go show you where that is. So if you're in SageMaker Studio, let me zoom in here. So you're in SageMaker Studio. Let me collapse this menu. So I'm going to look at that text generation endpoint. So you can see this is my model. I'm going to go to test inference. And then in test inference, I'm going to click test the sample request. And it should come up with a base right here. I think last time we did peanut butter. So let's do chocolate chip cookies. And let's capitalize this because that's just what I feel like doing right now. All right, we're going to send the request. Okay, and so that is the payload object that's going to hit this Llama model on your behalf. You can see the parameters that are defined right here. Over on the right-hand side, it's handling this. All right, it was a little too large, noted. And here's what Llama Chat thinks about our recipe for chocolate chip cookies. 4 cups flour, baking soda, teaspoon, unsalted butter, room temperature. Wasn't expecting that. White granulated sugar, brown sugar, chocolate chips. Yeah, that looks fair. Okay, so we got a provisional recipe for chocolate chip cookies. The reason why we're looking at this is I want you to look at this request caret right here. So this request dropdown shows you this request body, but it also has extra things that we need. So the endpoint name, and then lo and behold, the inference component name. So if you are getting errors in your LangChain and SageMaker connector, like I did until I figured this out, that you need to add an inference component, just go in here, copy this, hoof back over to your notebook, and then just add that to the endpoint keyword arguments. So your SageMaker endpoint object can take a few arguments, such as the name of the endpoint, your Boto3 client, model keyword arguments, and then endpoint keyword arguments. When you're working with llama models, you have to add this accept EULA, and then you should also add this inference component name. And then the content handler. Once you've done that, then we're going to build this mini chain here. That's just a summarization chain. And that takes this element function, and then the prompt, the model, and then the output parser. And I find it very healthy to make sure that your components are working nicely. So you can also just invoke the model. So you can hit this model, just grab the name, and then say model.invoke. Let's see if this is on our side right now. Great. Okay, so our model is definitely with us today. All right, so now we're going to generate text summaries. And so what's interesting is that, so LangChain actually does batching for you by default, which I think is pretty interesting, actually. So you can build this chain right here, right? We built the summarized chain, and then it's actually going to let us batch the responses just by calling batch here, which I think is really nice. So presumably that, I don't actually know, but I think what this is doing is using more cores on our machine to send a maximum of 5 requests for a single point in time. Although, I mean, it has to be doing this in a way that's not overloading my model endpoints, so maybe there's some intelligent timing on that batch. I'm not sure, but in any case, I appreciate that it has this batch by default. That's very nice. And so then to get summaries from our language model for both the text and the tables, this is what we're going to do. We run this function to send all of that in, and it just does it for us, which is really nice. And then again, we'll just check the first text summary. I mean, these numbers are odd, but the rest of it looks fine. So this is a figure, and then it's summarizing essentially the text that's probably below this figure, where they're sampling 10 to 20 trajectories for each input, and then computing the likelihood score for each of these pairs. So that's our first text summary. Let's assume that the rest of them are okay. Now that we have text summaries for both the text and the tables, we're going to use our local Lava model to generate summaries for the images in natural language. So that's what Lava is going to do. Lava is going to look at the pictures, and it's going to convert the picture into a natural language summary. And then the summaries are what we're going to use as our index, which I think is very clever. So great, we're going to loop through those JPEG files generated by unstructured. Let's go see where those are. So back in our working directory, which is right out here, the unstructured library is going to create this new folder called figures. And so figures is, just as it sounds, all of the figures from the image. So we saw this one, input sentences, trajectories, comparisons. Let's look at this one, another graph. Okay, great. So again, once you get all of those image packages installed, then this is what unstructured will do, that library. All right, great. So we have those figures. We're gonna walk through that list. We're gonna walk through the files in that directory. We're gonna send each to this local Lava model and have it generate a summary for us of what it sees in that image. So that's right here. So this I needed to write myself because, of course, the LangChain solution is pointing to just one model that does both language and image. And I decided to kind of split it up and do lots of different models. And so this one I definitely needed to write myself. So this is just an image summarize function which actually takes that whole Lava model that we downloaded earlier And then because it's all just sitting on my notebook, it just takes the path for the image and then the prompt. So we're just going to open that image, run it through that processor along with the prompt, generate the output, and then decode the output. And then remember, the decoding takes basically the probability distribution that comes out of the lava model and then converts that back into language. And so this is our message. The encoding into base 64, you don't need that for lava, but you do need that to build the database, actually the local Chroma DB that's going to actually index the images. And so that's where that's useful. Okay, and so next, just as promised, we're going to walk through this local path here, look at all the JPEG images, pick them all up, encode them, add them to the encoded list, and then summarize the image. Yeah, so then run that image summarize function, and we're going to pass in the lava model, the path, and the prompt. All right, great, we return this, run it, and then once this has finished running, here is just another sanity check. So that's that first object in the image summaries list. And I just removed this instruction syntax because it's a little challenging on the eyes. Okay, great. And so here's the summary. Image displays 2 bar graphs, each representing different data sets. The left is labeled number trajectories. The right graph is called temperature. The graphs are informative and appear to be part of a scientific or technical presentation. Nice job, Lava. Nailed it. Okay, so now we have summaries of the text, we have summaries of the figures, we have summaries of the images. Let's put all of these together into one vector store. All right, so now let's try to spell multi correctly. All right, so we're going to create a multi-vector retrieval store. And again, that's storing the text, tables, and images in this local doc store. And then we're going to store the text, summaries, and images in the vector store. And so this sort of dual storage that's going on here lets us first look up the vectors in this vector store. And then from the vectors, we're going to point to the documents. All right. And so to do this again, we need an embedding model. And so as I mentioned earlier, I went into SageMaker Studio and opened up the embedding model and deployed this onto an endpoint. And then same as for the chat model, you just need the endpoint name. No inference component name for the endpoints though, so that was a lot easier. Okay, so we're going to import from LangChain this multi-vector retrieval, point to Chroma. And then, so there's a different object actually for endpoint embeddings, which is this one. So SageMaker endpoint embeddings. And then from the SageMaker endpoints object and embeddings content handler. So get those 2 imports. And then this took a little bit of munging just to make sure that I had the inputs basically correct and that it was going directly to JSON. And I just had to modify the key basically to actually hit the right key. So that's the input. And then the outputs, same as last time, read that, load it into JSON. And then this one I also had to modify a little bit. So the function, the chain is expecting that this function is going to output vectors. And so just make sure that you output the vectors from this function directly. And in this case, that was model predictions. And then this embedding key hashes to the actual vectors. And so that's what I return. All right, great. So with that, we'll rerun the SageMaker runtime client. And then, as promised, just pass in the endpoint name, the client, and then that embedding content handler. So I should probably have named this embedding content handler because it might conflict with the earlier one that's also called content handler. So consider actually changing the names for those. All right, now we're going to create this multi-vector retriever. So this is going to take an in-memory store, this doc ID multi-vector retriever, which takes the vector store and the ID key and the document store. So again, 2 storage objects. One is the basically the vector store, and then the vector store points to the documents. So we're going to use the vector store to find the right document, and then we go and retrieve the document itself from the doc store. So then we're going to ingest the documents using this function that worked beautifully. Thank you, writers. And then add those. And then return the retriever. And then now we have this chroma vector store that works, and that has a name and the embeddings. And then we create the retriever. And then this retriever has the vector store, the summaries, the text for all 3 of our different parts. And then just to check that the vector store is indeed a valid chroma, and then the multi-vector image is also a valid object. All right. Now that we created those 2 vector stores, we're going to build those into the chain so that we can actually retrieve documents and then send them to the language models and get response back all in the same session. So we're going to put it all together here. So again, this needs the base64 image encoding to retrieve the images. And actually the chain is set up to also take images, but I just decided to only take text. So part of that is for sending in images as the core for the retrieval here. All right, lots of, again, helpful functions that worked very nicely. I was very happy. Okay, great. And then the text. So I changed this. So CJ built this to be a financial advisor, actually, that will look at documents about companies and give financial advice for those investment opportunities. I modified this to be an AI scientist. So this AI is an AI scientist tasked with giving examples on AI research projects. They will be given a mix of text, tables, and images, usually charts or graphs, and then use this to provide AI research advice related to the user question. And so the text, again, will take in the question, and then it's going to look at the tables. Okay, so now we'll build this chain. I was feeling a little bit lazy, so I just pasted the SageMaker endpoint right here into this multimodal chain. You could pass it as an argument, but it's a long notebook, so I just repasted it. So that's that chat model that we pointed to in the first case. And then we're going to set up the RAG pipeline here. So this is the whole chain that we're going to use to ask questions to this whole component here. So we have the context with the retriever, which uses this runnable lambda, and then the question, which is this pass-through. And so the retriever, of course, goes and retrieves the documents based on the vector, and then the question, of course, comes through from the customer. All right, so that's the chain, and that's sort of like setting key value pairs for the whole chain. And then we invoke this runnable lambda on the image prompt function, which then hits the model, and then we output it. And it worked incredibly well. Once I had things set up, it ran like a charm. Okay, so now we're going to check the retriever. And I asked my question, give me papers that are related to large language models. And I got 4 documents, and here was an image. And then I asked for papers that are related to multimodal retrieval, and I got 4, and here was the first one. All right, so I hope you enjoyed this multimodal retrieval demo. Let me get you some resources. All right, so 2 resources for you. So the first one, of course, is the documentation. And so that shows how to customize a foundation model by developing a retrieval augmented generation pipeline using SageMaker Jumpstart foundation models. And then the second link is an example notebook. So that example notebook actually stands up RAG with Amazon OpenSearch and then SageMaker. So feel free to check that one out. And then, of course, if you want to see the multimodal project, just check out the link in the video directly. And so that, my friends, is a wrap. I hope you enjoyed this video about multimodal retrieval augmented generation with SageMaker. I will catch you next time. Bye.